In this video, I'll talk about how we can actually try to make sense of our multiple regression model, which means that we want to do some statistical inference on that and do some tests and see if our model is actually a good model or not. So earlier, we looked at sums of squares, which capture the uncertainty in a dataset. And we defined the total sums of squares, the total uncertainty in our dependent variable, not taking any predictor into account, right? So there's no x or anything in here. The model sums of square, the distance between the line, or in the case of multiple regression, are like hyperplane, basically, our predicted value, minus the mean. And the residual sums of squares, which is the most important one, the distance from the line, or from the prediction. So this is how well our model is trying to predict the outcome, and this is the actual data. And we're interested in seeing how the variance explained by the model relates to the variance that is not explained by the model. But we're looking at that, for example, through the R ratio. To do this, we can use this sum square estimate to estimate the variances. Now, I said before that for calculating the explained variance, so how much variation is explained, we don't really need to divide it by anything to make it a variance, but it is easier to do, and we actually need to define the variance for the statistical inference test. So we need to somehow transform these sums of squares to variances. Now, you might remember that's dividing by n minus 1, but actually it is a bit more tricky than that. We can average these sums of squares to obtain what we call the mean squares. And these are pretty important because these are always in the output of the model. So we transform our sums of squares to variances just by averaging them, and we get something we call the mean squares. To average the sums of squares, we need to divide it by the corresponding degrees of freedom. This is a bit of a really hard and technical point. This is where the dividing by n is minus 1 comes from. When we calculate the variance over the entire data, it turns out we calculate the variance around like a line, it's a little bit different. I'll show it. So the mean squares is the sums of squares divided by degrees of freedom. But what are these degrees of freedom? We talked about them earlier in the t-test. You learned about degrees of freedom, but what exactly are degrees of freedom? So degrees of freedom are the number of values in a calculation of statistics that are actually free to vary. That sounds really weird, right? But it's basically from our data, how many of those values are actually free. So we can think of degrees of freedom as some sort of currency. So let's say we have a single degree of freedom for every data point in our sample to begin with. So if we have, let's say, 10 data points, we can see it as having like 10 points or 10 coins, basically, right? 10 money, whatever, yeah. 10 currency. 10 pieces of information, to be exact. Yeah. Any parameter we compute, that actually costs us some information as well, right? So this sounds a bit weird, but you basically, to calculate the sum of squares, we need the mean, right? Or actually, we need all the regression parameters, for example, for the residual sums of squares. So let's say we have n equals 5, yeah? And so we have 5 data points. So 1, 2, 3, 4, 5, yeah? And these are just 5 scores that we observe. Maybe happiness, yeah? Maybe a 2, a 5, a 3, a 1, and a 0, like some scores, right? These 5 values are information. They tell us something. They inform us about the happiness score in the sample. Now, to calculate a mean, we need something extra. We need, or to calculate a variance, right? We need something extra. We also need the mean, which is, in this case, well, 11 divided by 5. So is this 5.5. So for our variance, we also need this. Now, that's other information, but it's not actually information. It's completely made up of all these data points here, basically. This mean we need to fix. Because we get a mean, it doesn't mean that we actually got more information. And in fact, we lost some information in here. In fact, the information from our sample is just summarized in this mean. Now, if you have to calculate a variance, you have to keep this mean constant basically. If we know 4 of the scores, we already know what the last one has to be. So if I know this is 2 plus 5 is 7 plus 3 is 10 plus 1 is 11. So I know the first 4 scores are 11. And I know that the mean is 5.5. I know that this one must be a 0, because otherwise the mean would not be 5.5. So it's not like we get more information by calculating the mean. Actually, calculating the mean costs us a piece of information that's kind of in this mean, which means that this factor, then if you include the mean as known, has some less information. Because of this, the degrees of freedom to compute the sums of squares equals n minus p. Basically, every parameter costs one piece of information on the variance, in which p is the number of parameters used in the model. So the total sums of squares are based on a model with just a sample mean, a very simple model. That means that the degrees of freedom of the total model is n minus 1. So the residual sums of squares are actually, in this case, the same, they just regressed based on all regression parameters. So you have more than 1, you have p, so you have n minus p. Now the model sums of squares is, degrees of freedom of the model sums of squares is a bit more complicated. But basically, the sums of squares, the degrees of freedom of the model is the total one minus the residual one, or the difference between that. It basically means how many more pieces of information did we have comparing our regression model to the simplest possible model that we have, which we're also going to call a baseline model to compare to a model where we only have the mean and nothing else. So the model degrees of freedom equals the number of parameters minus 1, or simply the number of predictors. That's for the entire model. Okay, so that's all a bit weird, but let's look at some examples. So here I have, in this case, I have 1 data point, here I have 2 data points, and here I have 3 data points. And I'm going to try to explain here why the degrees of freedom are what they are. And let's say we have a very simple regression model, a null model or baseline model in this case, where the height of the line is simply the intercept. In this case, it will be the mean. Right, so the residual variance around this model is actually the same as the total variance. Right, in this case, SS res of this model equals SS dot. Right, the SS res depends on the model. SS dot is always the same. It always is around the mean. In the other case, it won't be the case. Right? So in this case, the degrees of freedom is n minus 1. Minus 1 because you have one parameter, the residual degrees of freedom. Right, and often when I talk about the degrees of freedom, I talk about the residual ones because that's the one that's most important. The residual degrees of freedom here is only is n minus 1 because we only have the intercept. Yeah. So why is this n minus 1? Right, let's consider a data set where we have 1, so n equals 1 data point. You would never have that, of course, but let's say we have it, okay? In that case, degrees of freedom would be 0. N minus 1, 1 minus 1 equals 0. So what does 0 degrees of freedom mean? It means that we cannot calculate a variance because we cannot divide by 0. You would get like some undefined value. In this case, it's very simple. We have one data point. Let's say that's, like 2, for example. Then what is the mean? Y bar equals 2. Because that's the same data, right? It's just the mean of one value is just that value. There's no other data. So the average is just going to be this one value. Then what is y minus y bar, which is going into the sum of square, is 0. Right? Because this mean is already, this data point already fed into this mean. If this is 0, there's no variation around it. It means that we just simply do not have any information to calculate the variance here. Right? We don't have anything to approximate the variance. Right? In this case, the variance in the data is exactly 0, but we want to use that. So we have a sample of 1. We want to use that to say something about the variance that we think is happening in the population, but we don't have any information about the variance in the population because we only have one data point. Okay. Now let's look at the next case. Here we have n equals 2 data points. So now the average is exactly in between the 2 points. Okay. It will be exactly the midpoint between them. And now we can calculate a variance, right? But from n is 1 to n is 2, we added only one piece of information. Okay? We don't suddenly add more than one piece of information. We only add one piece of information. We are able to calculate something that approximates the variance, like very badly, but it will approximate the variance, because we added one piece of information. And because of that, this variance is actually technically only based on one piece of information, not 2, right? Where here, the variance could not be calculated because we did not have any information. Here we don't suddenly have 2 pieces of information, we only have 1. We added 1 point, meaning we have 1 piece of information we added that allows us to estimate something in the variance. And this is why the degrees of freedom here is 1, not 2. Now we have n equals 3. Here we add 1 piece of information again, right? So we can estimate the variance even better. We have like 3 distances from the mean. But again, these distances are actually only 2 pieces of information that are making up these distances. If we know 2 of them, we know what the third one should be because we know the mean as well. So we don't actually have 3 pieces of information, we only have 2. And that's why degrees of freedom equals 2. And that's where this idea really comes from. That variance is estimate. If you want to, well, if we know that we have a sample, we want to generalize the population, we should take into account that we also estimated the mean and a piece of information went lost into that mean. And any parameter in a regression model really is going to eat up one of these pieces of information, if you will. So let's look at a bit more of a complicated situation. Here we have a simple regression model. We have an intercept and we have a slope with 1, k equals 1 predictor, right? And p, the number of parameters, is 2. 1 here and 1 here. Right, and again I have a situation where I have here in n is 1 case, 1 data point, here in n equals 2 case, 2 data points, here n equals 3 case, 3 data points. So what happens here? Well, first this looks extremely weird. I drew only a few possible lines, but actually now there are infinitely many lines possible. So we now have 2 parameters and we only have 1 data point. That means that the degrees of freedom that are associated with this model, the residual degrees of freedom that are associated with this model, are n minus p equals minus 1. Now you never want to have negative degrees of freedom. It means you have insufficient information to make any claim. In this case, we want to draw a line with 2 parameters to reproduce 1 data point. And we can do that in an infinitely number of ways. Okay. Let's say I have 1 data point. Let's say I have a 5 that I measure. Yeah, and I measure 2 here, for example. Right, so how can I reproduce 5 with 2 here? Plus, so for example, I could say 3 times 3 plus 1 times 2. Or 1 plus 2 times 2. Or 5 plus 0 times 2. And I can think of any combination of these two that will lead to the same result. This is something we call not identified or unidentified. It means that any of these lines would be possible. When you can think of any line here, any of these lines would reproduce this 1 point. Because of that, we can definitely not estimate a variance around it. We cannot even, we cannot do anything with this. This line, we cannot even estimate these parameters because it's not identified. We can get infinitely number of configurations of these parameters. So we cannot say the intercept and the slope is like, in this case, the slope could be 0, it could be non-zero. We don't know because they both would be equally likely or equally possible. So our degrees of freedom are n minus or -1, or the residual degrees of freedom in this case, and we just cannot estimate a variance, right? In this case here, for the linear regression model, here, if we have 2 data points, again we add one piece of information, right? We would get n minus p equals 0, which we also call saturated, which means basically perfect. We could draw only one particular line. We can draw exactly one line that goes through both points. Any other line would not go through the points, would be a reverse line because of that. Again here, okay, we can estimate the total variance, but we cannot estimate the residual variance from this line because both points are on the line, right? So y minus y hat, the predicted value, the height of the line, equals 0 for both points. Right? And because of that, we don't have enough information again to estimate a variance. We can estimate these parameters, but we can get them. But so we get one slope particular, but we can't actually estimate the uncertainty around the parameters. We don't know, okay, what's the uncertainty of the points around it. Only when we go to 3 data points in this case can we start estimating a variance. But now again, just because we have 3 data points doesn't mean that we have 3 pieces of information. Adding one data point here doesn't suddenly add 3 information, it adds 1 information. Right? So that's why here the degrees of freedom equals 1, right? 3 pieces of information minus 2 parameters. And that's why when we calculate this residual mean squares, the variance of the model around, the variance around the line, basically, the degrees of freedom in this case is 1, not like 3 or so. That's really where this idea comes from, and this is why we were dividing by n minus 1 when we're calculating the variance to begin with, which is actually just the total mean squares. Now you can even take it further. This is like, getting it more extreme, but you could even think a model where we have 2 predictors, so one here, and I add x squared as second predictor, which is something we can do. It will allow us to draw like a nice, like a non-linear line, which I'll talk a bit later about in the course. And if you can see here that if we don't have at least 3 data points, we have 3 parameters, we need to have at least as many data points as parameters, otherwise we can't do this. There's too many points that are possible. And only with 3 points we can estimate a line, but because degrees of freedom here equals 0, we can't estimate residual variance, which means that we don't have a residual mean squares, which means we can't assess if this is a good model or not, because we want to look at if this residual mean squares is going down. Okay, so that was a lot of information about the degrees of freedom, but I wanted to share that with you and explain where this comes from. So with the degrees of freedom, we can average the sums of squares that we have to mean squares, which are estimates of the variance. And what does this tell us? It tells us the variance of the total variance that we have in the data. This is already this S squared variance, it's the same thing. But it also tells us the variance that we have around our model, the uncertainty that we have left after taking our model into account. And the model mean squares, which is the variance that is explained by the model, if you will. Now we can use these to calculate what we call an F-statistic. And we calculate that by dividing the mean squares of the model, which is the total one minus the residual one, divided by the residual one. This statistics follows an F distribution, which has 2 degrees of freedom. Right, we have the degrees of freedom for the model and the degrees of freedom for the residual. So this distribution, like the T distribution, has degrees of freedom, but it has 2. And that's really important to know. You need to know which ones those are where they are in the output and which ones should report. And that's really very important. This is what this is all about. So the F-statistics follows under the null hypothesis. So if all the parameters are 0 basically, an F distribution with 2 degrees of freedom. And it has some sort of shape like this. It's always positive. So you see it's no longer a distribution that's like symmetrical, which means we can't do a one-sided test or so. It's always positive. And the higher it is, the more it's implied that the model is actually explaining some variance. And this is a distribution, so it means we can calculate like an area for which, let's say, alpha equals 0.05. It means we can calculate a point at which we reject it. And if you get an F value that's above this point, it's significant. So what can we do with this F test, or this F test statistic? We can use it to test a null hypothesis, a particular null hypothesis, that the mean squares of the model equals zeros. That means that the model does not explain any variance. Basically, that also means that we're testing that R squared equals 0. That the model is not explaining any variance. So for example, in our example we had 610.4 sum squared of the model, 443.6 sum squared of residuals. We just divide by 8 because it's degree of freedom. We get these values. And then we can calculate this F ratio by dividing them with each other. And we have to report it like this, APA style. Say F, open bracket. Here we put the first degree of freedom, which in this case is the model one. And here we put the second degrees of freedom, which in this case is the residual one. We get some test statistic and we get a p-value out of there, right? So here we got here 0.016. So this is what the output looks like in R, but basically in JASP you get this same table, and we'll look at that a lot in this course. We get, actually that's the coefficients where we should look at this one here, the F test. We get 11.01 on 1 and 8 degrees of freedom. So the degrees of freedom of the model and the residual degrees of freedom. And the p-value is 0.01056, which is significant, and alpha is 0.05. So then we would say we reject the null hypothesis that the model is not explaining any variance, meaning that we are significantly explaining variation in the data. So the F test can be used to see if a model explains a significant amount of variance. In the case of a single predictor, it's actually just the same as significance of the slope, and that makes sense. If you have a single predictor, you'll see that here, this p-value is the same as this. If we ask a statistical question in a different way, we're going to get the same answer. We're asking now a statistical question in two ways. We're asking, is this prediction of loneliness significant? Is this estimate non-zero? Well, yeah, there's a p-value associated with that. Or we're asking, is loneliness leading to a significant increase in explained variance? Which is the same question really, because if it's not, then the estimate would be 0. We get the same p-value. When we have multiple predictors, however, the F-test can be used as significance of the model as a whole. And that's really the cool part about it. And as we will see, what we can also do is we can define the F-test for testing if some parts of the model are significant. So now, what we did is we defined an F-test to compare our regression model with predictors to a model without any predictors. But we could also compare a regression model with some predictors to a model with some predictors fewer, and use the F-test for model comparison. For example, we can test, does adding a predictor improve the explained variance? Does adding a set of predictors, like 2 at the same time, improve the explained variance? Now that's really the strong part about the F-test, and this is why we need it. Like later in the course, we're going to talk about, let's say, 3 groups. That actually involves 2 dummy variables, which we'll show later. So that means that we want to test not the significance of one slope, we want to test 2 at the same time. And we can do that with the F-test. We can compare a model with those 2 parameters to a model without those 2 parameters and see if the model is better. F-tests are the most commonly reported test statistics in psychological research. We see them all the time. Much more even than t-values. F-tests are the things that are pretty much always reported. Almost, not every paper, but many papers use F-test. So that's why this is the most important thing to learn in this course, right? So the general linear model, all these models like regression, t-test, correlation, ANOVA, they're all actually special cases of this general linear model. Right? There's a multiple regression model with multiple linear predictors. The t-statistic in the general linear model tests if a single parameter is significant. So we use a t-value to test if, for example, one slope or one difference between means is significant. The f-test is used to test if a set of parameters is significant. Because for a single parameter, we can just already look at the t-value. That's really the most important use for the f-test. Technically, what we're looking at with the f-test is if the increase in r squared, if we explain more variance by adding some predictors. T-statistics are symmetrical and can be tested one-sided, but f-tests are not. So we can't have a one-sided f-test. F-test is really only looking at if we explain more variation. It doesn't look at if the effect is negative or positive. That's an important thing to remember for the f-test. All right. One thing we can also think of is the f-test as a way to compare models, and this gets a bit more technical. It already is a long video, so maybe take a break, take a sip of water before we continue with the next part. And this will come back. I'll explain this again next week as well. And actually, this is what we do in the entire course. So for example, we could say we have two models. We have model 0, where we have only an intercept, and model 1, where we have two regression effects, like so the intercept plus two predictors. Both models have residual degrees of freedom. Model 0 has one parameter, and therefore the residual degrees of freedom is n minus 1, which is the same as the total, right? Because it's just the variation around the mean. Model 1 has three parameters, 1, 2, 3, and therefore the residual degrees of freedom of model 1 is n minus 3. Because model 1 is nested in model 3, and model 0 is nested in model 1, model 1 will always have a higher explained variance than model 0. What does that mean? This model is already part of this model. Right, so we have here y equals b0, that's already in here. That means that this model will explain the outcome variable y well. Then so will this model, because I could just say, okay, then this is 0, this is 0. We get the same model, right? So M1 will always be better than M0. Always. It will never be worse, because if at worst it could be the same. It will always explain more variation. The question is this increase in variation significant, or is it due to chance alone? And that's what we can use an f-test for. The model sums of squares is the difference between the two, and the model degrees of freedom is the difference between the two. So that's why I keep saying the residual degrees of freedom and the residual sums of squares are the most important, because we can calculate this for every model and then just take the difference between them to get this model degrees of freedom and model sums of squares. Now what does this mean? We can use the f-test to see if we can go from one model to another model. We don't have to use this simple model. We could have another model where we say, okay, plus b1 times x1 plus error, and compare those models. Then we see that this is the same here, and we're actually using our f-test to test for this particular parameter, if that is explaining the variation more. In sum, the correlation test is just a form of simple linear regression. The t-test for difference in means is also just a form of simple linear regression. The multiple regression extends this to multiple x variables, multiple predictors. And it will turn out ANOVA is also just a form of multiple linear regression, because we just use dummy variables as predictors. In fact, almost everything in linear regression, really like a lot of things in statistics, things you might not have realized are just linear regression, and that's why we keep talking about this. And this is what we'll do in this course. It won't really get more advanced like this. We're going to talk about t-values to compare the significance, to test the significance of parameters, and f-values to compare models. And with that, I mean that we use f-values, for example, to test if a set of parameters are significant or if a model is better than another model. And we'll talk more about this in the next week. So that's it for this week video series.